Alright, the recording has started. So, welcome to week 5 of the problem solving session. And today we will continue with few more problems on material balance. Alright. A brief intro about myself, a PhD scholar in the Department of Chemical Engineering, and I have been like the TA for this course till the course ends. If you have any queries, you can reach out to me. My email is given, and I urge you to post any queries related to the course in the course discussion forum. All right. So every week we meet on Saturdays from 3 to 5 p.m. The recordings are available in the YouTube channel, in my YouTube channel, and the notes are also accessible. Are you able to access the notes? You last week you said you haven't checked it. So did you check it today or this week?
No.
No? Okay. But it is available, all right? Okay. So let's start with some like theoretical questions first. So read the question. The material balance equations are based on the law of conservation mass. Is this statement correct or
Yes.
not? Yes, you're correct. Then what about this? Which among the following are conserved for systems without reaction? Select all that apply. Tell me. Which among the following are
Mass of
conserved?
it. Mass
Yeah?
of individual compound.
Moles of individual components. Okay. If you recall the material balance questions that we have been doing, in a system where there is
No.
no reaction, so there will be input, I, output, and there is not, and the consumption term and the generation term, they are zero, right? Because we take a steady state assumption, so there is no accumulation at all. When there is no reaction, whatever is going in is basically coming out, right? So in that case, total mass will also remain conserved, all right? Total mass, like if we do an overall mass balance, and total moles also remains conserved. And similarly, so moles we take for gases usually um, of our when we are gaseous components, and mass we take usually for the solids or liquid components. So based on what components are involved and what state it is, people express their quantities in either moles or mass. So in that case, the individual components, either they are moles or mass, they are also conserved. So in a scenario when the system is not in the system, there is no chemical reaction going on, means nothing is getting consumed and no new product is getting formed. Whatever is going in, that thing is going to come out, right? So all of these things remain conserved. Now, which among the following statement is or are correct for an ideal continuous stirred tank reactor? Select all that apply. So you understand what is a stirred tank reactor?
Yes.
Yes. So in an ideal one, which of these statements apply or is applicable for a ideal CSTR? So, is the contents well mixed in an ideal CSTR?
Yes.
Yes. What about the concentration of the components? Are they same throughout the reactor, or do they change in the reactor?
It will change. It will
Within
change.
the reactor, it will change with will the concentration will change in the reactor, or will the
It
concentration of the components will remain same?
concentration change.
See, in an ideal CSTR, we assume that when the reactants are entering, so this is, let's say this is an ideal CSTR, when the reactants are entering, all right, as soon as they enter, they get mixed very well, all right, because of the stirrer. And what some reaction happens. So in that process, all the components, individual components, if you do individual molecule balance or atom balance, overall it will remain same. So there won't be any region where some components is higher and some components is low. So that's the ideal case when any at any maybe near the walls or at the center or at the corners, everywhere the concentration of each component that is involved in the reaction that remains same, okay, in an ideal case. Now what about the exit stream? Is the concentration in the exit stream more than the concentration inside the reactor, or is it the same as the concentration seen inside the reactor?
Same.
Same, yes. So whatever is coming out, here there is an exit stream, it will have the same concentration as the concentration that was present inside the reactor. So these 3 points are applicable only for an ideal CSTR. So let's uh, do some problems. Mm, yeah. So this question is on yield and selectivity. I'll give you a minute, have a read, and we'll continue. So, hello Shrikant. I'm seeing you for the first time. Welcome. So, we were just doing some problem, and this is the numerical problem that we have just started. I'll also ask you to read the problem that is given in front of you, and then we'll start the solving process. Done? Okay. So, these are the two reactions that are given. Uh, Here, ethane C2H6, ethane is getting, in the first reaction, it is getting converted to ethylene C2H4, and there is another reaction that takes place where the same ethane can also get converted to methane, all right, in presence of H2. So basically, two reactions are happening in a continuous reactor at steady state. So let's draw the reactor. Let me take a fresh page. This is your reactor, right? And here all the reactions will happen. There will be some feed and product. I'll come in a minute about what components will be there in the feed and the product. So the feed contains 85%, 85 mole percent of ethane and balance inerts. All right. So let's assume a basis of 100 moles. So I'll ask you at the end of today's session to solve a small problem, all right, on your own. That will be towards the end. Do you think you will be able to do it?
Okay.
Okay, great. So let's continue first this. So the basis, let's assume a basis of 100 moles of feed that is entering. As per this basis, you will see that 85 mole is ethane, C2H6, and saying that the rest is inert means 15 mole is inert, I. And the fractional conversion of ethane is this, the fractional yield of ethylene is this. Calculate the molar composition of product gas, the selectivity of ethylene to methane production. So this is the product gas. What all components will be there in the product gas? First, let's consider N1 be the moles of some component, some amount of ethane, N2 be the moles of ethylene, right? As per this reaction, as per these two reaction. Then hydrogen will also come out. So let's consider N3B moles of hydrogen, N4B moles of some moles of methane, and N5B the moles of inert gas. So this is the composition in terms of moles of product gas. All right. So do you remember in the last class we discussed about extent of reaction that is given by Xi, and we also discussed of about this expression where the number of moles of the any component that is coming out is equals to the number of moles that is entering plus, now if this component is involved in multiple reaction, we take a summation form where nu I and nu j, all right, is ij, this is the extent of reaction when nu ij is the stoichiometric coefficient of the component I in the reactions involved. This was the expression that we discussed in the last class. So we have to use this expression in order to um, like solve for the number of moles in the product gas, right? So for individual components like C2H6 first, what we see N1 is the number of moles that is coming out. How much is going in? 85 mole is going in, and C2H6 is present in two reaction. Let's label this reaction as one is R1 and there is R2 reaction. So in R1 and R2 both, in both of these reactions C2H6 is the reactant So the expression becomes where Xi1 is the extent of reaction for reaction 1, Xi2 is the extent of reaction for R2. Okay. Now let's do similarly for the other components. C2H4, the expression becomes N2 equals, we are not adding C2H4, so N in I naught is 0. So it will be just Xi1. If you are experiencing any doubt in understanding how I'm writing these expressions, let me know. For hydrogen, the expression becomes N3 equals Xi, Xi1 minus Xi2. For CH4, N4 becomes 2 Xi2. Okay, and for I, it is N5. Since it is inert, it is not participating in the reaction. So however much inert gas is coming in, that much will come out. So this will be 15 moles. Okay. So in order to get the values of N1, N2, N3, N4, and N5, we have to get the values of basically the Xi1 and Xi2. So how do we do that? In the question, if you read, it is given that the fractional conversion of ethane is 0.501. All right. So ethane C2H6 reacted in fractional form. It is 0.501. So fraction unreacted is 1 minus 0.501, that is unreacted ethane. Okay. So N1, which is the number of moles of C2H6, will then become 1 minus 0.01 Z2X6 unreacted, right? And um, divided by total moles of feed C2X6 in feed, right? Into how much entered, 85 moles of C2H6 entered. Understood how I wrote this expression?
No.
No? Okay. So here N1, that is the number of moles of C2H6 in the product, right? So that will become what? The amount of C2H6 that didn't react, right? That didn't react. So total, we know total C2H6 that is entering the reactor is 85 moles. Out of that, which didn't react, it will come out So 1.0.501 is the amount that didn't react. Since this is a fraction, so that's why I wrote as a ratio, right? That C2H6 unreacted by C2H6 that is entering the feed. Okay, so the from the total amount of C2H6 that is entering, which didn't react, will come out as a product gas. That is what this expression means. Understood? Any doubt?
Yes. Understood.
Tell me what's the doubt?
No, no, no.
No doubt.
Yeah, no,
Sorry, can you repeat what you said?
no doubt. Okay, fine.
No doubt. Okay. Now, if you calculate this, so let me get calculator. Into 85. That is around 42.4. So 42.4 moles of C2H6 is N1 that is coming out. Okay. Now we have the expressions as well that I have given. Let me number it so that we can refer it later on. So if we fit the value of put N1 in equation 1, so it will become 42.4 equals to 85 minus xi1 xi2. Okay, this is what it will become, or we can simplify this as well. Eighty-five minus 42.4 42.6. Okay, now in the question is one more information that is given to us. The fractional yield of ethylene C2H4 is 0.471. Okay, if you remember the definition of yield, what it is the moles of product. So in this case it is ethylene, desired product is ethylene, by moles of ethylene if the limiting reactant is completely consumed. So in this particular um, reaction, what do you think is the limiting reactant here? Which component is driving the reactions? Ethane, right? C2H6. The entire reaction or both the reactions are
Yes.
dependent on ethane. So considering that fact, let's first compute the maximum yield. that is the denominator part in this expression, the maximum yield of C2H4 in the case when the reaction completes, like completes according to the stoichiometry. So 85 moles of C2H6 is entering. Now suppose it gets completely consumed, means for 1 mole of ethylene we get 1 mole of C2H6. Means the reaction proceeds as per stoichiometry. Then we should get 85 moles of ethylene. All right. So this is the denominator value. The yield means if we, and what is the product? The numerator will be N2. So N2 by 85. All right. And we got the value of yield, that is 0.471. So from this expression you can calculate the value of N2. So you get 40. All right, you get 40 moles of ethylene. All right, so this 40 moles of ethylene, since from expression 2, this is expression 2, we get the extent of reaction for equation for reaction 1 will be also 40 moles, and we have this expression now. So let's label it as expression 5. Put in 5. So we get Xy2 as 2.6 mole. Okay. So Xy1 and Xy2, they are calculated. We got the value of N2 as well. We got the value of N1 as well. These two values are obtained. Now we need to only get the values of N3 and N4. N3, which is number of moles of hydrogen, is Xy1 minus Xy2, that is 40 minus 2.6, which is 37.4. N4, which is the number of moles of methane, it is 2 into Xy2. Xy2 is 2.6, it is 5.2. So now we have the complete composition of product in number of moles. But they have asked for the uh, molar composition, but we can also calculate the product gas composition in terms of percentage as well, mole percent, because as you see, the feed is given as mole percent. So if we calculate the values of or the composition of product gas as mole percent, that will be much more accurate. So it's very easy to do it. I'll not show the complete process, but you just have to calculate the total number of moles, which is a summation of N1 plus N2, N1 plus N2 plus N3 plus N4. plus N5. If we add it, then you should get 140 moles, all right, total. And then product gas composition in percentage will become first uh, percentage of, let's say I'll do one, okay, then the rest you can will understand and you can do it on your own. So let's say for ethane percentage, it will be 42.4 by 140 into 100. It will be 42.4 divided by 140 into 100. It is 30.28%. Similarly, the percentage of ethylene is 28.6%. Percentage of H2 is 26.7%. So I'm basically copying the values of the percentages that I have obtained when I practice the question on my own. All right. These values are calculated values. Don't think I imagined them. All right. So if you do it after this class, you should get these values. So this gives the product gas composition as mole percent. And if you add them, you should get 100%. All right. Now we are also asked to find the selectivity of ethylene to methane production. So selectivity of ethylene to methane will be calculated as like this. So we know the number of moles of ethylene by number of moles of methane, CH4. So ethylene, it was N2 by N4 basically. N2 is 40, N4 is 5.2. It will be 40 divided by 5.2. So 7.7. Okay, 7.7 mole C2H4 by mole CH4. This is the selectivity. Any doubt?
So understand.
Understood? Great. Now move on to the next question. Oh my god, why does it look like this? Okay, no issues. Okay, this is a better representation. All right, this is the question. All right, first quickly have a read. So, did you read the question?
Yes.
Yeah. Okay. So, I hope you're now able to get that this is a question that we can easily solve. Only new thing that in this question is equilibrium constant. So, how will we use it? Let me show you. So, there is this equation. This is your chemical equation CO plus CH2O gives this is a reversible reaction CO2 plus H2, right? And we are given the fact that um, at equilibrium, what temperature T is equals to 1105 Kelvin, the equilibrium constant is 1. Okay, we know this. And you know the definition of equilibrium constant? It is the mole fraction CO2, mole fraction H2 by products. All right, this is what we are given. We have to find we have to find the equilibrium composition and the fractional conversion of the limiting reactant. So what's the limiting reactant? If you see, we are given that the reactor within the reactor, the feed contains 1 mole of CO and 2 mole of H2O. So which is the limiting reactant here?
See.
CO, right? Okay. So we have to find out the fractional conversion of CO. Now, in order to calculate equilibrium composition, we have to take the help of extent of reaction expression. So let xi e be the extent of reaction at equilibrium. Okay. So at equilibrium, individual number of moles for individual components will become, or let's say CO will become 1 mole was entering, 1 mole was entering initially, right? So 1 minus xi e, this is for CO. For H2O, 2 mole is entering minus xi e. For CO2, in the feed there is no CO2, so it will be 0 equals to xi e and N2 here also equals to xi. So if we just calculate or find the value of xi e, we can get the value of individual compositions. Okay. So in order to get xi e, we have to take help of this expression of equilibrium constant. So at T is equals to 1105 Kelvin. K is 1. So 1 is equals to the mole fraction. So what will be the mole fractions? Corresponding mole fractions. So YCO2, it will be xi e by total number of moles. What's total number of moles here? If you add NCO, NH2O, NCO2, and NH2, what is the total number of moles here? 3, right? So mole fraction for CO2 will be xi e by 3. Mole fraction for H2 also will be xi e by 3. Mole fraction of CO will be 1 minus xi e by 3, and mole fraction of H2O will be 2 minus xi e by 3. So we have to put these values of mole fraction in this expression. So we will get an expression containing only xi e as the unknown. Okay, so you should get a quadratic expression, by the way. I'm just cross checking. All right, for this will get cancelled. 2 minus 3 xi e is equals to 1. So xi e will be 1 by 3 or 0.67. All right, moles. This is the value of xi e. Understood? It out?
No.
No doubt. All right. So this is what I got for xi e. You can cross check it later on as well. Now, if you put the value of xi e, you'll get individual mole fractions of CO, CH2O, H2, CH2O, and CO2. So for CO, it is 1 minus xi e by 3. For H2O, it is 2 minus xi e by 3. Here only it is by 3 H2, and similarly for I 3. Okay. All right. Any doubts? No? No, right?
No.
No. So these are the individual mole fractions that we got. Now what we see is the fractional conversion of limiting reactant. We have to find out the fractional conversion of limiting reactant, that is fractional conversion of CO, we have to find out. Let's try to do that. Now at equilibrium, we have already we know the composition of CO. It is 1 minus 0.33. This is the number of moles of CO. Now this number of moles is basically corresponds to CO, that is unreacted. Okay. Since we have to find the conversion, so it will be 1 minus 0.67. This is the CO that has reacted by the number of moles which has entered. 1 mole of CO has entered in feed. So it will be 0.033 is the fraction. Alright, any doubt?
Mm.
No? Okay. So that's it. That's the end of this question. So this is another question, this one, question number 6. But this question I would ask you to uh, solve later, right? Towards the end of the class, after I have solved all questions. You can try on your own. If you are not successful, then I'll discuss it. All right. So I'm skipping this question for now. Now, I'll solve some questions where in the flow sheet there are three processes involved. First is recycle means one some portion of the product, it basically is recycled back or taken out and put back into the feed stream. That is recycling. Bypass. Bypass means some portion of the feed doesn't enter the process, rather it is directly added to the product. This is called the bypass stream. Whereas purge, what is purge stream? Here, two things is happening. From the product, some portion is taken out and recycled back into the feed stream. And from the recycle stream, another stream is coming out that is called purge stream. So the concentration of the purge stream and the concentration of the recycle stream is same. Okay, so these are the processes or the flow charts, how they look like when someone says that this is recycled back, this is bypassed, or this is purged. All right, this is how the flow charts would look like. And we will have to do material balance around some junctions where the bypass is done or where recycling feed is coming out in order to get the values of the maybe the total amount is recycled and all. So I'll discuss few questions based on these concepts. Okay.
What is the per?
What is purge? Okay, so sometimes what happens, no, um, when recycling is there, some product, some amount of the product is taken out, okay, and put back into the feed, into the recycle stream as well. Maybe in order to reduce the amount or remove the unwanted stuff, they remove some of it. That is purged. Like additional thing is removed, some amount is removed from the recycle stream. So I'll explain a question, discuss a question on this per stream. It will be much more clearer. All right.
Okay.
Okay. So let's discuss this question first. I'll give you a minute. Have a read. Uh, you continue reading it. Let me give me a minute. All right. Okay. This is a question on bypass. Okay. And let's read it first. So there's this fresh juice that contains 15% solid and rest 85% is water. It has to be concentrated to contain only 40% solid by weight. Now, in a single evaporation system, it is found that volatile constituents of fresh juice escape with water, leaving the concentrated juice with a flat taste. In order to overcome this problem, what they are doing, they are adding some part of the fresh juice, all right, into the product stream. So this stream is the bypass stream. It is escaping the evaporator or the process and getting directly added to the product stream. So you have to find out first what is the fraction of the juice that has bypassed the evaporator, and next the concentrated juice produced. What is the amount of that per kg of fresh juice fed to the process? So this is the flow chart for the process. If you so we have to do basically material balance, write some material balance equations. So there are unknowns x, y, z, and p. These are the unknowns that corresponds to the stream values or the kg of uh, let's say for x is the kg of fresh juice that is getting, you know, that is entering the evaporator. Y is the kg of juice that is bypassing. Z is the kg of juice that is leaving the evaporator, and P is the concentrated juice mass that is finally getting formed. So you have to find the values of x, z, x, y, z, and p. So for that we would need four equations, and to do that we have to write material balance equations. So let me quickly draw the process here so that you can refer to it more quickly. X is entering, Y is the bypass juice, this is the feed, Z is leaving the evaporator, P is the product. In the feed, there is 80 15% solid. If we just write the solids, 15% solid. The bypass juice will have the same concentration as the feed, so it will also contain 15% solid. Z that is leaving from the evaporator now contains 55% solid. Now, since the product is getting diluted due to addition of the bypass juice, it contains 40% solid. So before we start writing the material balance equation, let's consider a basis of 100 kg of fresh feed is added. Okay, so first do a material balance over separation of the bypass feed. So if you see feed F is 100, we have taken a basis of 100 kg of fresh feed entering. This feed is getting bifurcated at this point. So we are doing material balance. This we are writing this particular expression over this particular point. So 100 kg is entering, and what is coming out? X is coming out and Y is coming out. Now, similarly, if we do material balance, over the evaporator. Means let's consider only this particular portion, this portion. So what we see, X is entering for solids, material balance of solid. So X is entering, but 15% means 0.15% of X is solid. And what is coming out? 0.55% solid is coming out. That is Z into 0.55. This is expression 2. Now let's do a material balance over this point where the bypass stream and the stream coming from the evaporator is getting mixed and you get the product. So if you do a overall balance at this point, you'll get Z plus Y equals P. If you do solid balance over this point, you'll get 0.55C plus 0.15Y is equals to 40% P. This is expression 3, expression 4. 4 unknowns and 4 equations. Okay, now we have to solve these 4 expressions and get the values of x, y, z and p. So how do we start? How would you start? Suggest a way. You can do it in multiple ways, so there is no correct way in this. Means the all there is correct way, but there are multiple ways to start. 'So it's just algebra, right? You just have to solve this algebraic expressions. So I'm thinking to first use expression 1 and 2. So from expression 1 and 2, what I say is x is equals to 100 minus y, and x is also equals to 0.55z by 0.15. So that is 3.67 z, right? So we can now use this. Now let me write this as expression 5. Now we can use this in expression 3 and 4. All right. How? Let's do it. Let's substitute z first from 5. So z can be written as 100 minus y plus y equals p. This is z can be written as 100 minus y by 3.67. That is z. Similarly, rewriting equation 4,
So now you have expression 3 and 4 in terms of only two variables. That will help you like simplify the process. Two variables, two equations. So first let me simplify these. This one.
Hello? Hello?
Ah, yes, 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 I'm here. I'm just solving. Do you have any doubt? You can see my screen and you'll understand what I'm doing. But other than that, if you have any doubt, let me know.
Your screen is not working.
Sorry, sorry, can you repeat?
Your screen
Hello,
is not
can you
visible.
repeat what? Yes, yes.
Your screen is not visible.
Okay. Can you see my
Screen not
screen now?
screen not visible.
Screen is not visible.
No, it's stopped actually.
Okay.
It's stopped
Okay.
actually.
Okay. Let me reshare my screen. Can you see my screen now?
No.
Can you see my screen now? Hello. Can you see my screen now?
It is visible.
It is visible. Okay. So I have got the value of P, which is 37.5 kgs. As you can see, similarly, value of Y would be 2.67 into 37.5 divided by 100 minus 0.67p minus 100 divided by 2.67. Is 14.09. So Y, that is the bypass juice weight, is 14.09. P we got, that is for the product. Now we can easily get the value of X and Z as well. From 5, what we see, X is equals to 100 minus Y. Y is 14.09. It gives 5.91. Similarly, Z is 100 minus Y by 3.67. So 85.91 by 3.67 is 23.41. Okay, these are the values of X, Y, Z, and P and Y. Using these values, you can get the values or the answer the part A and part B. So part A asks for the fraction of joules that bypass the evaporator. So Y by 100. 100 is the total fresh feed that is coming. A will be Y by 100 into in percentages they have asked. So it is 100%. Y is 14.04. So 14.09% is the fraction that has bypassed. And what is the concentrated juice produced per kg of fresh feed? It is basically the value of P, that is 37.5 per 100 kg of fresh feed. Alright, any doubt? Do you have any doubt? Yes, are you there?
Yeah. How
Yeah.
much total feed and how much total output?
So the fresh feed that is going in is 100 kgs. We took that as a basis, as you can see in the beginning. Okay, it was not given to us, but we had to consider it. Otherwise, we couldn't have solved the problem. So
Correct.
the
Yes.
fresh, yes, that is going in, and the output is for P. For output is P. So we got the value of P as 37.5. This is the input for the overall process and output for the overall process.
37% output. That is the
37.5 kg is the
that
weight of the concentrated.
that is for that is 40% solid.
No, this is the total weight. In this, there is 40% solid. 37.5 is the total weight of the product, in which 40% is the solid content and rest 60% is water.
So how much water evaporated?
How much water evaporated? So
That is
you can, that is
70.
in the process only. That is in the process you can see. So 85% water was there, 60% water is remaining in the product. And even also you can see that in X, that is in the feed, it contains 85% water, and here 45% water is there in Z that is coming out. So around 20% water loss is there due to evaporation. But the bypass stream also contain 85% water. So the water in the bypass stream and the water content in the feed that is coming out from the evaporator, these two added up and increase the water percentage at 60%. I can show you in terms of values as well. Hello, there is some disturbance from your side, some long beeping sound. Can you hear me? Is there any issue with your mic or something like that? Yes, whenever you're switching on your mic, there is this beeping sound. So I'll quickly show you in terms of values as well. So 85% water is entering the evaporator, right?
Hello.
Yes, yes.
Now it is okay.
Now it is okay. Yeah. Like I'll quickly show you in terms of values as well. So in the evaporator, 85% a feed containing 85% water is entering, right? So that means X we know the value of X is 85.91. So water entering evaporator is 0.85 to 85.91. So 73.02 is the kg of water entering the evaporator. Then what is leaving? Z is leaving. So water leaving 45% will be water here. So we know the value of Z, 0.45 into 23.41, 10.53. So if you subtract these two, you will understand that this much amount of water is like evaporated, like left the system, which is around uh, close to 63 kgs of water has left the system. But still the product has very high amount of water because of the bypass stream that has entered. So bypass stream has 85% water, so it is getting mixed with the stream coming from the Z. So overall product will now have around 60% water. Make sense? Does it answer your question?
Yes.
Yeah. Okay. So this is another question that I have, but it looks like it is not completely written. This is another question. Okay. In a proposed process for the preparation of methyl iodide, 200 kg per day of iodic acid is added to an excess of methanol. This is the reaction. Hi is the iodic acid. If the produce contains 81.6 weight% of CH3I, right, and along with unreacted methanol, and the waste contains 82.6 weight% of iodic acid and 17.4% water, calculate, assuming that the reaction is 40% complete in the process vessel, the weight of methanol added per day, and the amount of HI recycled. So this is a recycling problem. While you think about the flow chart, like how the flow chart would look like, you start drawing it. Give me a minute. I'll just quickly come back. All right.
Okay.
Okay. Let's begin this problem. Okay. So this is a recycling problem, but with a chemical reaction. So there is a reactor in which this reaction is happening. Hi plus CH3OH gives CH3I plus H2O. This is the reaction that is happening there. Now it is said that the feed contains 100% HI, and what is this amount? They have given around 2000 kg per day. 100% is there, and it is around 2000 kg per day. And also methanol is also coming in another stream. So let's call this stream as M, that contains 100% methanol. What is leaving as a product? P. The product contains CH3I along with unreacted methanol. So CH3I is around 81.6% and CH3OH is 18.4%. Okay. Now two things are happening. There is a waste coming out and some amount is also recycled. So from the product, two streams will come out. One is waste and some amount of product getting recycled. Now recycled product has only HI, whereas the waste W has 82.68% HI and 17.4% water. 82.6% HI and 17.4% water. So this is how the flow chart would look like. There is a recycling stream involved here along with the chemical reaction. So what's the limiting reactant here? The question states that there is an excess of methanol. So the limiting reactant is HI. Right? From the question itself, we can understand that. First, let's convert it into one unit like moles so that we can do the rest of the uh, calculations easily. So first, take a basis of 100 kg of product. In that 100 kg of product, there are two components, CH3I, CH3OH. In 100 kg, there is 81.6 kgs and 18.4 kg of methanol. This question is a bit tricky, all right, I'm telling you before, so please pay some extra attention there, okay. The molecular weight of CH3I is 142, and the molecular weight of methanol is 32. So kg moles will be basically 81.6 divided by 142 and 18.4 divided by 32. So I've already calculated this. So it is 0.575 and it is also 0.575. This is the number of moles, individual number of moles of CH3I and methanol in the product stream. Now, if you see the stoichiometry for generation of 1 mole of CH3I, you need 1 mole of methanol. So equivalent kg mole of methanol it is you need to complete this reaction will be like, so 1 mole, similarly 1 mole of similarly 0.575 moles of methanol we will need to get 0.575 moles of CH3I. The total will be 1.150. This is the total number of moles that you uh, basically will get equivalent, okay, as a when this reaction completes from this particular reaction from this particular reactor. You will understand later why this step is important, okay? Means it will make sense, it will start making more sense to you, but please pay attention. So let's consider for the waste. So let's consider a basis of 100 kgs of waste and convert the given mass fractions into moles, number of moles. Similarly, Hi is there and H2 is there. In kgs, it is 82.6. This is 17.4. Molecular weight of Hi is 128 and the H2 is 18 kg moles. Basically 82.6 divided by 128. So it is 0.646 and 17.4 divided by 18 is 0.968. So we got a number of moles. Now, the next question that I'm going to ask is what's the total Hi entering the reactor? For this, we'll consider a basis of 100 kg of waste. Why this question is important? You see, per day around 2000 kgs of Hi is entering, but let's not consider one day as a basis. Just the basis is here for 100 kgs of waste. But at this particular point, some Hi is entering from F and some Hi is entering from the recycle as well. Okay, and here the Hi is getting bifurcated. Some is coming out as waste and remaining getting recycled. We have to understand how much of Hi is actually entering into the reactor. So how will we calculate that? In the product stream, sorry, in the waste stream, there is 0.968 kg moles of water. So 0.968 kg mole water per 100 kgs of waste W. Okay. For the reaction to complete, you need 1 mole of water, and for every mole of Hi, you are generating 1 mole of water. So 1 kg mole of Hi gives or generates 1 kg mole of water. So this two will get cancelled. With this one and this one will get cancelled. But we need to get the Hi entering the reactor in kgs. So for that, we need to consider the molecular weight. 1 kg mole of Hi corresponds to 128 kg Hi. That means these two will get cancelled out. Now the value that you'll get corresponds to kghi per kg waste. So it will be 0.968 into 128 divided by 100, 1.239. Or you can just write it like this. Um, wait, you don't need to 0.968 into 128. This is 123.9, so let's consider it as 124 per 100 kg waste. Okay. Now for so this is we got for basis of 100 kgs. So now what will the total number of HI will enter? In 100 kgs of waste, 124 kg of HI is there, and here 82.6 kg of HI is also there. See what is happening. This is the stream that is coming out from the reactor. It is getting bifurcated, alright, into two parts. One is recycled and one is product. Now the product stream, there is no HI. That means HI total is only present in these two streams. We have this for 100 kgs of waste, we have 82.6 kgs of HI that is coming out, plus in the recycle, since we don't know the weight of HI that can come out from the recycle stream yet, so we took the help of stoichiometry in order to estimate what could be the corresponding value of HI that can enter. So that is why we wrote this expression. This is given to us, the first part is given to us. This we took from the stoichiometry second part, and then in order to get the value in this form, we consider the molecular weight of HI. That is why we are adding these two parts. So when you add it, it will come about 206 kg of HI is entering per 100 kg of waste per 100 kg W. Okay. If there is doubt, hold it. Okay, I'll I'll address your doubts at the end. Now, what is the amount of CH3OH that will enter? So HI is there, CH3OH is there, the product CH3I is coming out, the water is coming out as a waste. So CH3OH will enter the feed in the recycle. In the recycle, there is HI, and let me read the question again. Hmm. Okay. The product stream only has the methanol that is coming out. Some methanol is coming in due to the reaction to start the reaction, and in the product stream there is methanol. So that's the thing. Now we'll use again the stoichiometry in order to understand how much CH3OH is entering the reactor for per 100 kg of waste. Basis is again 100 kg of waste. So for 1 mole of CH3OH, you are generating 1 mole of water. So and in the waste there is 0.968 kg mole of water in 100 kg of waste. 1 kg mole CH3OH reacted, here reacted, will generate 1 kg mole of water. Okay. Now here, if these two CH3OH and CH3I, some CH3OH will come out, whereas remaining CH3I will remain unreacted. So the amount, the number of moles of CH3I that has been used to convert into CH3I is equivalent to 0.575, and that has not reacted is again 0.575. So this part is reacted component, reacted number of moles. This part is unreacted. Now if you add this is the total number of moles of CH3I that you would need to complete this particular reaction according to stoichiometry. So that is what it meant. So 1.150 kg mole CH3OH reacted plus unreacted. Okay, divided by how much is reacted? 0.575 into, there is one more component that will come. If you see, this 2 will get cancelled, this 2 will get cancelled, and we have to cancel kg mole of CH3. So for doing that, I'll consider the molecular weight of CH3OH, which is 32. So 32 kg CH3OH corresponds to 1 kg mole of CH3OH. So this will cancel this as well. So now if you compute it, keeping 100 kg waste constant, basically 0.968 into 1.150 into 32 divided by 0.575. So you should get 61.9 kg CH3OH. Okay, for 100 kg of waste. Okay, now why these values are important, it will be clear again in a minute. Let's consider a basis of 1 day. So per day, around 2000 kg of HI is entering the process, correct? And how much waste is getting generated? 206 kg, 206.6 kg of HI is getting entering for 100 kg of waste. So we can write it as for 100 kg of waste, we are getting 206.6 kg of HI, and for 100 kgs of waste, you are getting 61.9 kg of CH3OH. 61.9 kg. So this expression will help you get the weight of CH3OH that is entering per day. So it is 2000 into 61.9 by 206.6 CH3OH that is entering per day. So if you solve it, it will be 599 kg CH3OH per day. So this is the value of M. Okay, this is the value of M. In the question they have asked us to get the weight of methanol that is added per day. So part A is done. Okay, around 600 kgs of methanol is added per day. Now part 2 we have to find out the amount of HI that is getting recycled. So we have to find the value of R here. See, in order to do that, we have to consider the fact that 40% of the reaction is completing in the process. Okay, 40% of the reaction is getting completed in the process. That is the fact. Here, limiting reagent is HI. That means only 40% of HI is getting reacted. Rest 60% is remaining unreacted. So if we do 40% HI is getting reacted, 60% unreacted. If we do material balance, about the reactor, by for HI, for HI, by about the reactor, I mean around this portion. If you do material balance, then what we get for the component HI, feed 2000 kg feed is entering plus R contains also HI. Alright, now these two is the total HI, but here since it is recycling and then it is coming back, at this point the percentage of HI will be 0.6. Okay, again 2000 kg of HI is entering at here, and it is getting mixed with R, but the final amount that is entering the reactor contains only 60%. Rest 40% here at this point is getting consumed. It is coming out, it is getting consumed. So this is a cycle, right? That is why this is inlet. This is inlet. Now what is outlet? About this, here R is coming out, here R is coming out, plus in the product stream there is no HI, but waste is coming out, right? So 0.826 0.826% of waste. So what's the value of W? We can calculate that. That is generated per day. So it will be 2000 kg of HI getting entered per day, and here for 100 kgs of waste you are getting 206 kgs of HI. So this means per day how much waste is getting generated? 2000 into 100 divided by 206.6. So it is 968 kg waste is generated per day. So this will be the value of W here. 968. So now I think it should be making sense, like why we calculated uh, the amount of HI entering the reactor for per kg of waste, or the amount of CH3OH entering for per kg of waste, because it helped us later on to calculate the values of CH3OH and waste for per day basis using these expressions. Okay, I'll upload these notes, all right, and you can have a look at it again. If you have any doubts, you can let me know in the next week session. So if you
Yeah,
solve this, sure, okay. So I told you, right, it's a bit tricky. It also took me a minute to understand this particular question, but once you understand, it's not that difficult. You can try to do it in a different approach as well, where you can write algebraic expressions by doing by writing balance equations for individual atoms, like I, then O. So like that you can do material balance expressions as well. This is one approach, but you can try doing on your own with that approach, where you write material balance equations for individual atoms like I, O, H, carbon, like that. So let me finish this. So 2000 into 0.6, 12, 120, seven, 99.568. So, so 1200 minus 199.568 is 0.4. R, R will be divided by, so it's close to 1000. So you're getting around 1000 kg